opportunity to, oh, I forgot to mention that. Thank you, Janelle. So for some of us who have not gotten a hands-on skill in solar installations and design, this is a very good opportunity to start. After this class, you'll be able to have adequate knowledge to even go out and then try this out, for the very first time. So let's make this interactive. If at any point you have a question, please notify by raising up your hand, or you can just, softly interrupt, and I'll give you the chance to ask your question. Usually when I want to start this kind of program, I usually want to start with the concept of sustainability or sustainable energy. It has become a buzzword. Some will also, there has so many terminologies around this. You hear energy transition, you hear net zero, you hear so energy sustain. I mean, so many, you hear green energy. So what is all of this? I summarize every one of this in just simple diagram that we have here on the screen. So when we talk about energy sustainability, most times we talk to people about sustainable energy, the first thing that comes to their mind is solar. And it's not, the reason is obvious, because I mean that's something they can easily relate with. They can feel it, they can touch it. When you talk about inverter, solar panels, battery, yes, these are the things that they can see and they can feel. Now we're even talking about hydrogen. We have green hydrogen, we have blue hydrogen, we have gray hydrogens. This sounds abstract. I don't think anyone, among us have maybe seen hydrogen fuel before, or hydrogen, in the pure form when it has been splitted through electrolysis. But of course, we'll talk about now, hydrogen is a renewable form of energy. But of course, solar is something that we see, even when we pass through the street, we see solar system. But of course, that is not the starting point when you're talking about energy sustainability. The starting point when you talk about energy sustainability is energy efficiency first, okay, before you now talk about renewable energy. And that's why in this graph, you will see that first line of action is less energy via energy efficiency gain. So before you can even talk about how you generate your energy sustainably, you need to first of all look at the system that you want to power. You need to look at the demand side. When you're doing energy sustainability, you don't start from the supply side, and that's the mistake. That's where we get it wrong. The Western world, they have done a lot of work on the demand side, and now they're on the supply side. But we, from the developing countries, we've not done much work. Sorry to say, we've not done much work on the demand side. And what I mean by doing much work on the demand side, it's actually what I mean much work on the demand side is actually reducing the losses, reducing the inefficiencies in our system, reducing the whether technical or human error or human behavior in the demand side. So we have to first of all eliminate that, and that's what energy efficiency helps us to achieve. And in doing that, you need to conduct an energy audit. That's why we first of all started with energy audit costs. Now we are coming to renewable energy. So energy audit has to do with demand side as well as supply side, but more on the demand side, depending on the industry you're looking at. So when you've done all of that, then you can now see clearly what your demand is, your useful demand, what your useful demand is. Then you can now begin to think and begin to wonder how you can be able to meet that demand sustainably from renewable energy sources. And that's where you see this other green area where you have to do greener energy via promotion of renewables. So this is just the concept of sustainability. I just wanted us to get that clear. So the next place I want to touch on is energy cycle. Energy cycle. Energy sources of energy and the law of energy conservation. I'm sure many of us are already aware of, or many of us already know what the law of energy conservation is, which is energy can neither be created nor destroyed, but it can be transformed from one form to another. But in this whole arrangement, in this whole process, in this whole transformation, what is the primary source of energy? The primary source of energy essentially is the sun. Okay, so then through the sun, during our early stage in development, during the science classes we had in our early stage of development, we were told how the green plants convert sun energy into food or into glucose, which we eat from the green plant. through a process known as photosynthesis. So through photosynthesis, green plants convert sun energy into food, edible food that we can eat. And that's how plants actually grow. So from there, both humans and animals feed from this. Okay, and that's how we derive the energy that we use to talk, we use to walk. There are different forms of energy, by the way, but all of this energy comes from the food that we eat, both plant and animal. And in the end of our life cycle, everyone is committed to the Mother Earth, whether plant, animal, or human beings. Everyone is committed to the Mother Earth. And it takes millions of years, not thousands, not hundreds, millions of years for these dead bodies to convert to crude and gas, oil and gas. It takes millions of years, about 350 to 400 millions of years to convert to oil and gas. And because of the limited knowledge, because of the man's quest for industrialization, we need to industrialize, we need, the form of energy that we can use to power our industrial transformations. There was limited knowledge at the time, and the emphasis is on limited knowledge. So man now indulged in oil exploration, okay? The discovery of crude oil as far back as whatever year it is. And then they found crude oil, they found a way to explode extract the crude oil, and it went under refining process. And the whole purpose of this is to power our economic activities, right? And remember, I said that this is happening because of the limited knowledge at the time, but over years, over thousands of years, man has now realized that this is becoming a problem. Okay, it's now beginning to cause global warming, and global warming now leads to climate change. And if we continue in that trend, it will get to a point where our children might not be able to survive. In fact, it's already happening. It's already affecting us. We that are still, grown up on this planet Earth, right? No matter where you are on the face of the universe, climate change somehow is affecting us. How much more if we continue in this trend? How much more? What's going to happen down the line maybe in the next 50 or 100 years? So that has now led to a unanimous call at the global level, to curtail climate change. Okay, so that's just a background of climate change and the push for energy transition into renewable. So this is just to lay a background anyway. So I've talked about the law of energy conservation. Energy does not remain in one form, in the same form always. Now, to cause change, energy itself changes from one form to another. So during this change, energy is always conserved. It is not created anew nor destroyed. This is known as the law of energy conservation. We already know this, so I just have to move. So one of the things I also want to clarify is energy and power. Energy and power are like husband and wife, but they are not the same. Okay, for many of us who are even highly technical, sometimes we mix this up. So it's very important that we clarify this early enough. Power is, now I'm just going to define them by their units. I don't want to go into the, terminological definitions. So let's just use the units to understand this. In our other class, the energy audit, I think I went a little bit deeper into this, but this is just to brush up. So power is watts or kilowatts, whereas energy is watt second or kilowatt hour. So in energy, there is a time component. Power is like a momentary something. You cannot consume power. Is that I mean, so what you actually consume is energy, right? And not the power. So the power is like, okay, the capacity, but energy is actually when you now begin to use those capacity, right? So energy has a time component, and that's just the difference. It has a time component, whereas power is kilowatts or watt. Energy is watt second or kilowatt. Okay, so having that as at the back of our mind, what is the cost of 5 kilowatts continuous operation in a year? Now, this is energy. What you're actually paying for is energy in your homes. The utility energy bills that you're paying is for energy, not for power, right? So I don't want us to waste. This is a simple mathematics that we can solve. The solution is here. You get the material. If there's something you're not clear about, you can always ask questions, but I don't want us to spend. This is a very simple calculation. Let's proceed to the renewable solar system that we are here to discuss. So let's now dive into the solar PV application and design. All I've been saying is just to lay a background, and more like also to summarize the energy and electrical basics. Okay, so let's jump into the solar world. So photovoltaic is a technology which generates electricity directly from the sunlight. Remember when I talked about the limited knowledge in the other time, okay? And I said because of the limited knowledge, they have to now extract oil from the ground. But now, because of the advancement in technology, more research, into technology and innovation, man has now found a way to directly harness their energy directly from the sun. Okay, so instead of having to extract the crude oil that has been sequestrated or stored underneath the earth, man has now found a way to convert energy directly from the sun and use it to power the economic activity. And that's why we are here to talk about. Okay, so photovoltaic is a technology which generates electricity directly from the sun via a photovoltaic effect, photoelectric effect. Now, the photovoltaic model, which we call the solar panel, which is made up of photovoltaic cells, transform solar energy into DC electricity first. Your solar system, your PV panels don't generate the alternating current. We have two types of current. We have DC current, we have AC current. So the form of current that is produced by your PV panels are direct currents, okay, your DC current. So there's another form of solar energy, which is another solar energy technology, is also solar thermal. Solar thermal uses solar energy to generate heat rather than electricity. So let's bear in mind there are two forms of solar energy here. You have the solar photovoltaic, and then you have the solar thermal. So the solar thermal is what generates your hot water. You put it on your roof. It uses the heat from the sun to heat up your water, and that water is supplied into your home, and that's what we call solar thermal. And another one is solar panel that convert the sunlight into electricity, and then it's also supplied into your home. That is solar electricity. It is important to make a clear distinction between these two different technologies, which are often confused since they use the same energy source, which is the solar radiation. The electricity generated using solar PV can be fed into the electricity grid. That is when you have a grid connected system. It can also be stored in battery for later use, or it can be used directly. So this is just a picture illustrating these two forms of technology. The first one, you have the solar panels, and you have this smaller one here is the solar thermal that produces the hot water. You can have both in your home, and then you can reduce your dependence on the grid drastically, or even off the grid if your installation is adequate to meet your household energy demand. So we have two kinds of connections when we're talking about solar PV systems. We have off-grid. Off-grid means that the system does not have interaction with the grid. It does not have relationship with the grid, or you have grid-connected system. Now, what is most common in Nigeria is the off-grid system. Now, please, I must clearly state here that when you have an inverter that switches automatically between your grid and your solar system, that is not a grid-connected system. Please, I need to make that clarification here, because I know some might begin to wonder, okay, since you have an inverter that you connect both the grid and both your solar PV system, then that might want to qualify it as a PV, as a grid connected system. No, please. Your inverter does the isolation. So at one point, your inverter is connected to either the grid or to your solar system. That is an off-grid system, just so that we're aware of that kind of system configuration. So we have grid-connected systems that, like I said, that are connected to the grid. Now, this is not common in Nigeria. I'm thinking right on top of my head where we have this. There's a project in Kano. I was also involved in that project, 10 megawatts solar project somewhere in Kano, Kumboto, Kano State. It's meant to provide electricity to an industrial area in Kano State. I don't know if it's functional or but that is a grid-connected PV system, 10 megawatts. Is a grid-connected system, right? We also have a project somewhere in Abuja. The Ministry of Transport, then when Fashola was the minister, he initiated that project somewhere in Mabushi. Now, that project is not grid-connected. It's off-grid system. It's a large project. I think it's over 1.something megawatt, but it's off-grid. Now, because during the weekends, the offices are not working. During Saturday, Sunday, the offices are not working. So what that means that all the energy that is being generated by that project is not being used, it's not being utilized. Now there's a conversation between the ministry and AEDC, which is the local utility company in Abuja. There's a conversation between them to see how they can integrate into the grid, so that during the weekend, this energy that is generated from that solar system will be transferred into the grid, and someone else can use it and pay for it. So I'm just giving this illustration to help us understand what a grid-connected and off-grid PV system is. Okay, so let's move on. So these are different applications of PV off-grid and then PV grid-connected systems. I don't think I will spend so much time because I think I've already explained this to an extent that everyone should understand it. So there are some of them that are now for most off-grid PV system, which even in Nigeria, most of our installations are off-grid system. Now I'm just going to talk about PV off-grid applications. So you have some of them that are used for rural electrifications. Most of the mini grids that we have in Nigeria, those are off-grid, right? They are mini grid. Okay, so they're not connected to the national grid. So in that sense, we still regard them as an off-grid system. Okay, they're not part of the entire larger grid. Okay, we could reach a point where they could have interconnected mini grid. So in that case, they are grid connected. But in this case, when they're isolated off grid, so they're entirely off grid. So we have systems with batteries, and we also have systems that are without batteries. We have standalone mini grid, like I just already explained. We have purely PV system, and we have a hybrid system. Some of these mini grids are integrated with generators, so that if the supply from the grid, from the solar system is not sufficient to meet the load, generator kicks in. This happens automatically. So we also have large PV diesel hybrid mini grid for industrial applications. So what I explained to you that that is happening in Kano State is meant to service an industrial estate, right? But again, that is going to be grid connected, not off grid. So these are for grid connected application. You have distributed PV system feeding electricity onto the low voltage grid. You have residential rooftop. So somewhere in Germany and in other developed countries, what they do is that as a household or as a homeowner, you could actually put solar on your roof. It can be 3 kilowatts, it can be 5 kilowatts, it doesn't matter, but again, you can connect it, you can link it to the grid, right? Without battery storage, you can just connect it. So during the day, when you're out of your house, you're in your workplace, you're in your offices, and the solar PV is generating electricity. So what happens is that it transfers that electricity into the grid. So industry can use it. It's more like a like an aggregation. I mean, if they have so many homes that have achieved this, who have done this, they connect it into the grid. So during the day, the industries are up and running and they use it to work, to produce. Then at night, when the sun is no longer available, and at that time you will have retired back to your home, what the utility company will do at that point is to run their generators to supply you back that electricity. So at the end of the month, you can now check who has given more, who has collected more. And then if you have collected more from the grid, if you have used more from the grid than you gave to the grid, you pay for the difference. But if you have given more to the grid than you collected, you actually get some payment from that. Okay, so it helps the rapid adoption of solar system in those kind of countries. But because we have a weak infrastructure, we have a weak grid in Nigeria, it is still not very possible to do that in Nigeria. So you also have central PV systems. I think there was a time Nigeria tries to work on this. I think the conversation is still ongoing. We have about 13 or 14 companies who bidded for a kind of grid integrated solar project across Nigeria. Perhaps they were not able to reach a financial close, but I know that discussion happened, and I think it's still ongoing. So this for a central generation where you generate a large pool of energy from one location and you integrate it into the grid, more like your gas generators. So let's move forward. This grid connected configuration, I don't think I will have to spend time here because I've already explained what this means. But if you are still not very clear, you have questions, please let me know. Otherwise, I will just move ahead. I have explained this to a good point. So this is a central connected PV system. This is where you have to in a particular location generate large pool of electricity. Some people also call it solar farm, and then you integrate into the grid. This is a schematic of a grid connected PV system. So you have a PV system. In most of this grid connected, you don't need battery, except if you want to store some of the energy for your own consumption, but you may not need battery. So you have a PV system, and then you have your inverter. Remember, the PV generates DC current, so you have an inverter to convert it to an AC current, which is the form of current that is supplied by the grid. They also meter it so that you know exactly how much energy you're throwing into the grid, and then you feed it into the grid. So you may also want to put some level of protection. So this is a main fuse for protection, and then this is a diode to manage the flow. So we have an off-grid configuration. I will not also spend much time here. But again, in off-grid configuration, in most of the cases, you will have a battery storage system so that you can be able to store some of the energy for your later use. Maybe at your night time when you're not around, you want to use your battery. And one thing that I also want to talk about is your charge controller. So charge controller, because now for some of us who have background in electrical engineering or who understand electricity, you know that voltage is very, very important. And this is why it's important for some of us to look at the first foundation training or foundation course that Engineer Uche talked about, so that you don't get confused. We'll begin to talk about voltage, current, different voltage levels, because at that class we discuss all of these issues. So your batteries operate at a certain voltage. You could have 12 volts, you could have 24 volts, you could have 48 volts, depending on the voltage, right? So what your charge controller actually do is that it helps stabilizes the voltage that comes into your battery, because if you don't have this charge controller, your solar panel voltage can vary, right? But you need a charge controller to actually keep the voltage constant depending on the voltage of your battery. But again, what it does, if you have excess voltage, it converts it to current. And again, this is where you also need to consult our previous class, because we know electricity is equal to voltage times current, right? So the product of voltage and current gives you your electricity. So if the voltage is high, it converts it to current. In us, the output, the electricity output remains the same, only that your charge controller is now manipulating the voltage and the current. That's what charge controller do. We'll get to that. When we get to the design, we'll talk more about charge controller and how to size charge controller. But this is just an introduction and general knowledge about the system.
Well, I don't know whether you can say something about that combiner bus, because it's becoming a very huge component of the PV system, especially for those central and large scale.
Okay. Thank you, Engineer. So this is a combiner box, right? So in PV system, in some of the PV system, you could have arrays of PV system. You could have strings of PV systems. So you have, depending on the configuration of a PV, we're going to get to all of those configurations. Maybe that's where we can now talk into more details about the combiner box. But essentially, what the combiner box is, it helps you combine different strengths of the PV system who are going to feed into your inverter system. So it helps you to combine them, combine different streams of your PV wires. It helps you to combine them more like a junction box that collect from different feeds and then combine them, and then feed into your inverter or charge controller, as the case may be. Okay, so we can still talk more about this as we proceed. So this is an off-grid configuration. Like this is more like a replica of what we call mini grid. So mini grid, you have the power is generated centrally, and then you use a mini grid distribution network to take it to your load points. Some of the mini grids also have generators because it's possible that the weather might not be able to produce sufficient energy to power your load. So in those kind of situations, you have to, bring up your generator. So let us look at the components of a PV system. And we're going to start from the primary component here, which is the solar panel. So selected technical characteristics of silicon wafer-based and thin film solar panels. So we have different kinds of solar panels. Chief among them is the silicon wafer-based and the thin film. Okay. Now on the silicon wafer-based solar system, we have the polycrystalline and we have the monocrystalline. Now, some of us who are already familiar with this know that monocrystalline is better than polycrystalline in terms of panel efficiency. So monocrystalline has a higher efficiency. Now, this efficiency means that the amount of sunlight that is falling on that solar panel, the quantity of the sunlight that is converted to electricity or DC current, DC electricity, that's what we call as the efficiency. So the output, which is the DC electricity output, divided by the amount of sunlight that is falling on the solar panel. So we all know that generally the efficiency of solar panel is still not high. It's still in their 20s. Yeah, I don't think it has gone, although there's a lot of research work going into this. So it is possible that somewhere some might have gotten higher, but on
Chima, they are hitting 30 now.
Okay.
Yes, they are hitting 30.
Yeah, so
but for the higher from 600 watts, 1000 watts, all those Canadian solar, they're hitting 30 now. And who knows, it might go up.
Yes, just so you understand that there's still a lot of research work, in this field. For some of us who are interested in research, the efficiency of panels is still, still a work in progress. So, but for monocrystalline panels are doing better. They are leading in terms of, efficiency compared to polycrystalline. Okay. Then these solar panels, they behave differently in some kind of climatic conditions. Right. So temperature, as we are going to see, as we proceed with this course, we are going to see that temperature is a factor that affects your solar panel. Somebody might say that it is counterintuitive, that because you need sunlight to generate electricity. Now, I'm coming to say that temperature affects, essentially, higher temperature reduce the efficiency of your solar system. Right. So somebody might want to ask, so how can you have high intensity of sunlight without the temperature going up? It sounds counterintuitive, but we are going to get to that conversation. But essentially, this is where thin film solar panels gain strength. The thin film solar panels, they have a higher tolerance for higher temperature. So as the weather temperature goes up, it reduces the efficiency of your mono and polycrystalline solar panel. Okay, but this thin film has a higher tolerance for higher temperature, right? So it might be well suited in a high temperature region where the sun is hot. You might want to consider the use of thin film. That is when you do some consideration and see that, okay, maybe this high temperature might reduce significantly the effectiveness of your monocrystalline or your polycrystalline. You might want to consider that thin film. And of course, I think this market share would have changed. This source is coming from Renewable. This would have changed. Now monocrystalline is more in the market. Is the prices because of innovation research? The prices of solar panels has dropped, and this monocrystalline, the price before now, the price difference between polycrystalline and monocrystalline is the price difference is much. So because of that price difference, people prefer to go for polycrystalline, because if you look at the efficiency gain, the difference in efficiency gain is not so much compared to the price difference at the time. But things has also changed. So this market share is not updated. This something that happened in 5-6 years ago. So this market share is not updated. So the PV cell is the core component of a PV system. Since it's generating electricity, there are many different types of PV technologies, but I've already explained it. So let's just move ahead. So PV cell, the PV panel that we know today is made up of PV cells. So the small boxes that you see here are the PV cells, okay? And when you put up these PV cells into the panel, you now form what we call the PV module. Now, when you combine several number of PV modules, you form what we call the PV array. So just so that we know that when somebody mentions PV cells, you know what they're talking about. If somebody mentions PV module, you know what they're talking about. And if somebody mentions PV array, you also know what they're talking about. This PV array can also be string. So we are going to talk about it in this module as well. So an inverter converts direct current into direct current input from the PV array or battery into alternating current. I think I've talked about what inverter do. Your PV panels produces direct current, but you need an inverter to convert it to an AC current, before you can feed it into the grid or before you can use it in your home. Assuming your home is most of the appliances we use in our home are AC appliances. So that's about it. So let's talk about different types of inverter. Now, these types of inverter is we want to classify them based on at the point which you need to install this inverter. So by the configurations where you actually place these inverters in your design. First of all, we have a micro inverter. Micro inverters are inverters that are attached to the PV system. They are directly connected to the PV module. Okay. E.g. up to 300 watts. So these are inverters that you can attach behind your PV module. So every module has an inverter attached to it. So this is a micro inverter. It has its advantage and of course its disadvantage. So the advantage of this is that if there is a shading or if there's a problem with one of your PV panel, it may not affect your design. The problem will be limited and contained on that panel. It will not affect every other panel, right? So that is the advantage. If you don't use this kind of inverter, if you use other kind of inverter that I'm going to talk about, there is high chance that if one of your PV panel has a problem, it will affect all of your PV panel. If you have 50 PV panels and one of them have problem, maybe one of them has shading or one of them is damaged, it will reduce the output from the 50 panel. Okay, so in that case, this micro inverter makes sense. But of course, the disadvantage that it is more expensive because you need to buy this inverter or you have to, get this inverter has to be attached to all of the 50 PV modules. So this is the downside of it. So we have what we call string inverter. String inverter is more like an array where you have maybe you have 50. Maybe so, for example, you have a system that requires 100 panels, 100 PV modules. You connect 50 of them into as a one string, and you connect another 50 as a one string. So that 50 that you have is connected to one inverter. The other 50 is connected to one inverter. Okay, so that is string. So that 50 that is connected to one inverter is called one string. Then the other 50. So in this case, you have two strings. So that's what string inverter. So you have multiple PV panels, certain number of PV panels that are connected to one inverter. That is string inverter. They will have a central inverter. Central inverter, instead of having a string inverter, so you have two inverters that are connected to 50 PV modules each. You now have the 100 panels connected to only one inverter. So that is what we call a central inverter. This central inverter, you can use it in a solar farm, in a large grid connected solar. Even at that, it's still not advisable. It's for most applications they use string inverter. So they group certain number of solar panels, they connect it to one inverter. They have another group of solar panels, PV modules, they connect to another inverter. So these are the different kinds of inverter in terms of sizing. So let's look at mounting structures for your PV system. So the fundamental requirements of mounting structures are that they must support
Hello,
the weight.
sir.
Okay, please, somebody.
Yeah, you were talking about, sorry, my name is Maje Kodomi. You were talking about string inverters, and you were saying that you have several PV modules connected into one string. But you have some inverters that you are able to connect more than one string to that particular inverter. So what kind of system would you call that? If you understand what I'm trying to say, you have inverters that have different ports where you can connect different strings into.
Okay. So there's what we call interactive inverter. Okay, so there is possible that you could have a design that has different kinds of, depending on the configuration of your design. Okay, it is possible to have an inverter, then you could have another interactive inverter. Interactive inverter is more like an intelligent inverter that manages, is like it controls, what happens in every other inverter. So
yeah,
it's
more like a brain box.
Yes. So it's possible to have such kind of design.
Okay, thank you.
Okay, you're welcome. So the fundamental requirement, okay, I was talking about the mounting structure, and this is very, very important. The fundamental requirements of mounting structures are that they must support the weight of the PV module. They must distribute. For mechanical engineering, this will be very, very familiar when you're doing your design, your building design. Or for even civil engineers, you need to balance out the load and all of that. So that's something applicable when you're doing your solar PV designs. So they must distribute the load evenly on the roof or to the ground below, and they must withstand expected extra loading, maybe from wind or from snow, if it's a snowy country. Now, the thing is that for most of the building, at the time they were designed, many years ago, they were not designed to support, maybe it was not anticipated that the extra load that will come from PV panels will be placed on the building, right? Now, I'm talking for some buildings that are weak, maybe aged buildings or buildings that are, the structures are not strong enough. So you must consider the supporting structure. If the building, because of course you see some buildings where you have to place panels on all these roof surfaces. Now, when you combine the weight of all of those solar panels, you find out it's something that is significant. Now, if the building is not, or even the roof, it may not be the roofing structure of the building may not even be strong enough to support that the weight of that panel. So it is important, to examine that before you even go ahead and mount your solar panel. So since large array structure, including modules, are heavy, it is necessary to seek the advice of a structural engineer before prior to roof mounting. The structure should have.
Jim, sorry, 2 hands are raised. I don't know if it's a mistake or.
Okay.
If your question has been answered, you put it down. The other person is Galaxy A72. Can you change your name, please? Edit your name. Chima, I'm sorry about that.
Okay.
Barry, is there a question you have? Your hand has been raised for long.
Yeah, I even sent a question in, just not to interrupt with the flow of discussion. I sent it on the chat board also, because that time when it was when you were talking about the inverter anyway, because you said something that sometimes some people, when you put inverter with the PV connection, that people call it a grid connection. That is not a grid connection. And then the off-grid, that's very simple. That is very correct, because we don't need inverter for that one. So my question was, if connection with inverter is not a grid connection, and then without inverter with battery is an off-grid connection, how do we clearly, as a mechanical engineer, I'm not an electrical engineer, how do I clearly define grid connection in a very simple term? Because, like I said, if you understand what I'm saying, because when you are doing the explanation, maybe I didn't get it right, but when you are doing the explanation, you try to put it clear that some people mistakenly said when there is an inverter with a PV connection, that they call it grid connection, and that is not a grid connection. And then you explain the off-grid connection, which is very clear. So now my question was, how do I define grid connection then, if with inverter is not a grid connection?
Okay, let's make it fast. Sorry, Nachima. When you say grid connected, it means there is a two-way information system between you and the grid. It means you can feed to the grid can feed you. In the case of inverter, it doesn't exist. So I don't know if that you say in a simple terms.
Sorry, can you repeat that again, please?
Okay, I say in a grid connected, there's an interaction between yourself and the grid. In the case of the inverter in your house, there's no interaction between the inverter and the national grid. The inverter is just there to convert, and that's all. And maybe to change from the solar, it's just like to alternate, like what I said in the chat box. So the simplest way I would say is that in a grid connected, there's an interaction with the grid. In the case of the off-grid, there's no interaction whatsoever. Just like we talked about some PVC, some inverters that function like in form of like a brain box you have in your car to know the orientation of your sunlight, you know, whether it's west or south, so they can easily interpolate and they can easily know when the sunlight have already gone on the south side. They will optimize the PV system on that side and on this side. So that is how I would say, just capture it that way, that like in Germany, for instance, people, you can feed into the grid and then you can feed, if the grid can feed you, and then you can feed the grid. But in the case of the inverter you have in your home, you can't feed into the system. I don't know if that answers your question.
Okay. So in a nutshell, or in summary, when the inverter is able to take water being generated, the DC that have been generated by the solar PV, back to the grid for that interaction, that is the grid connected, right?
Yes.
Okay, and is it two ways that?
Yes,
maybe
it's two ways if it's smart.
Okay.
Yeah, right. Thank you.
All right, thank you.
Thank you very much for the question, and thank you very much, Engineer Uche, for clarifying that. Engineer Uche, please, my eyes may not be on the chats box, so please help me keep an eye on that. And if there are questions, help call my attention to it. I may not also see all the hands that are raised, so just help me with that. Okay, so thank you very much. Let's continue with the system structure, the mounting structure that we're talking about. So the structure should have an optimum orientation and tilt angle. Have I gotten to this one? Okay, yeah. So the structure should also have optimum orientation and tilt angle to maximize power output, and all shading should be avoided. The structure would typically be made from aluminum or galvanized steel. Painted steel and wood are also options, though such structure will probably require more maintenance over the 20+ years lifetime of the system. So whatever structure you want to use, you know, to mount your PV panel, you should put heavy consideration on the lifespan of that PV model. So you don't go and use wood as your mounting structure, wood that probably in the next maybe 5 to 10 years, it will give way, you know, for a panel that is going to last for as much as 20 years plus. So it's important to make sure you use a proper mounting structure for it. Besides looking at the building structure making sure that the weight of the panel can be evenly distributed on the building or on the structure that you have, and making sure that that weight is also properly transmitted to the ground, so that even in the case of maybe wind or other extra weight that may come upon the building or upon the panels will not, you know, lead to structural defects of the panels or the structures. So it's very, very important to look at that. So have different mounting structures. It could be ground fixed, it could be house roof top, and it could also be commercial, this for maybe commercial industries. But there's something I think I didn't stress here. Is talking about optimum orientation and tilt angle. So now we've talked about mounting your solar panels on the roof. Some would then ask, okay, the roof has already been constructed and the tilt angle doesn't align with the kind of tilt angle I want my solar panels to be. So what do I do? So in such case, you're not going to tell the homeowner to go and change his roof because you want to put solar panel, because the cost of doing that obviously outweighs whatever benefit you're going to get, the extra benefit you're going to get from getting the right tilt angle. So in such situation, you just go ahead and mount your solar panel in those kind of roof, unless if there are space on the ground. But of course, in most of these cities, you know, ground is a premium, you know, so it may not make sense to just put solar on those, except maybe perhaps if you have a carport where you could just use them. So I just wanted to stress this point. It's also bolded, you know, in this presentation. So we have different kinds of mounting structure. So solar panels can be installed on a fixed support or on a tracker. Now, tracker will help you yield more energy from that solar panel. Essentially, the tracker will follow the sun path. As the sun moves, as the sun rises in the east and sets in the west, the tracker will follow the sun path to make sure that it gets the maximum energy yield from that solar panel. That's essentially what the tracker do. I will have the different kinds of rotation. You have the one that does maybe linear rotation, then maybe from east to west, and then you have the one that can also rotate maybe about 360 degrees. So you have different kinds of trackers. So trackers are motorized structure that follow the path of the sun. I was talking about single axis and two axis tracker that follows the sun so that I can actually get the maximum yield. So let us look at the physical aspect of a PV system. So let us look at PV system and some of the things that you see when you look behind the PV system. When you look at the back of the PV system, you see some labels, some, you know, the nameplate, you see some. So let us try to explain what they mean. Essentially, what is more important to most people is what's the rated watts of this PV system. So it could be 300, it could be 400, it could be 450, depending, right? But as a professional, it's also good that you'll be able to talk about some of the things because they're not putting those details for fancy sake, right? They're putting it for you, who is a technical person, to look at them and then interpret them and then also see how best you can put those PV models to use. So let us look at electrical PV, electrical power. So by basic, you know, definition of power, you know, power is equal to voltage times current. Voltage times current. The current is measured in amperage or ampere, while the voltage is measured in volt. So essentially, let's also keep this in mind. This is the basic formula for calculating power. And that is what PV actually produces. PV produces power. But let us look at how PV works, you know, between voltage and current to actually gives us this power. It may sound academic, but it's also important. So under normal sunlight condition, the PV cell's voltage remains fairly constant. So when the sun comes out in the morning, right, and begins to shine on the PV panel, the voltage remains almost constant. In some cases, you might see voltage of 36, 35 volts. So, but it remains constant, right? But what actually changes when you say your PV panel is not producing much electricity, or at some point it's producing more electricity, what is actually changing is the current. So current changes with the, you know, intensity of the sun, but the voltage remains almost constant. Not that it is constant, it remains fairly constant, you know, throughout the period. So that is about voltage. So current is what actually changes. So under normal sunlight condition, the PV cell's voltage remains fairly constant. However, the cell's current is very sensitive to sunlight intensity. So higher solar irradiance will produce a higher electrical current. Lower solar irradiance will produce a low electrical current. So let us be clear on this. When your PVs are not producing as much electrical current it should produce, is because of the sunlight, you know, irradiance, and nothing to do with the volt. So another factor that actually helps your output of your PV is the surface area. So if you have more surface area exposed to the sun, you eventually have more current from your PV system. So two factors here is the sun's intensity and the surface area determines the amount of power or the amount of energy you could get from your PV system. So this is just a summary of that. So there is something we call the IV curve, current voltage curve of a PV system. So let me explain. These are just explanations so that when you're reading, you can also, you know, make reference to this diagram. But let me just explain this diagram. While I'm doing that, I might just read some of the explanation from what I have on the slide. So this red line that you're seeing here is actually it actually describes the power output from your PV system. Okay. Now let me explain the coordinates of this diagram. So on the horizontal, you have the voltage. On this horizontal, you have the voltage. Whereas on the vertical, you have the current. Okay, so we know that the product of current and voltage is what gives you your power. That is, power is equal to voltage times current. Now, this red line that you're seeing here is your power output. So this red line is a product of voltage and current. That's what this red line is. Okay, but let us look at it closely. Okay, when your voltage, now remember here is your voltage. When your voltage is zero, that's when you have your maximum current. And a product of maximum current times your zero here will give you zero output as power. Okay, now let us twist it again. At the point where your voltage is highest, now this is your maximum voltage. When your voltage is highest, your current is zero. So you have a maximum voltage, zero current. Maximum current, zero voltage. In either case, your power is zero. This is your power. Your power is equal to voltage times time. Voltage times current. If any one of them is zero, your power will be zero, in as much as this is maximum. So the question is, at what point are you going to balance these two to have the highest power output? If you put this on highest, you have zero. If you put this on highest, you have zero. So how can you combine these two to have the highest maximum power output, right? And that is where the concept of maximum power point comes to bear. Some of us, you will be hearing MPPT charge controller. What do you think is MPPT? Maximum power point tracker. That's what it means. That's what MPPT means. So it's find a place in this power line to maximize your current and your voltage to give you the maximum power. And that's what MPPT is. So now let's define some terms here. Okay. When your current is maximum, at this point where your current is maximum, what we call this is short circuit current. Short circuit current at the point where your current is maximum and your voltage is zero. We call it short circuit current, or ISC. ISC, short circuit current. And the definition is where your current is maximum and your voltage is zero. Okay, now you will see that when you pick any PV panel, look behind it, you will see all of these informations. I'm just trying to make us understand what those informations mean. So when you look at the voltage side of it, at the point where you have the maximum voltage and your current is zero, that is where you have your open circuit voltage, or VOC. So the definition of open circuit voltage is where you have your maximum voltage, but your current is zero. That's your open circuit voltage. Then at the point where you have your maximum power point, that's the combination of your current and your voltage that gives you the highest power output from this system. That is where what you have there is IMPP. That is current at the maximum power point. And this is where you have it. This point, this is where you have it. Now look at what's going to happen. If you move from this point, if you try to move down, what you're going to do is that you're going to be increasing your voltage, but again, you're reducing, sorry. If you move down from here, your voltage will continue to increase, but your current is reducing. If you try to move up from here, your voltage is reducing, but your current is increasing. So this is where you have the maximum power output from this PV system. And that's where we call IMPP. That is current at the maximum power point, or VMPP, voltage at the maximum power point. And charge controllers that can help you do this is what we call MPPT charge controllers. So at the MPP, that is the maximum power point. That's here you is a combination of your maximum power point voltage times your maximum power point current, give you your maximum power output. I hope this is clear. It might look a little bit confusing, but like I said, I have the explanations here on your own self-study. You read it, it explains this diagram. Now, let us look at the factors affecting power output. factors affecting power output of your PV system. So there are three critical factors which affect the instantaneous power output of your PV or module. One of them is irradiance. I think we've talked about irradiance on the surface, the intensity of the sunlight. One of them is temperature of the PV cells. I talked about the temperature. I think we're going to also explain that down the line. You have electrical load resistance connected to the PV cells or module. So let's look at the impact of irradiance. Now, going back to the IV curve. So the output of a PV panel or module directly depend on the solar irradiance incidence on its surface. So as irradiance increases, the current increases due to the increase in the level of photovoltaic effect. Okay, now this is our PV module. This is our PV IV diagram. Okay, now remember when I said that once the sun comes out, that the voltage, now this is the voltage line. When the sun comes out, the voltage is relatively or fairly constant. So now the temperature has moved. Okay, this is irradiance. Okay, not temperature. Now we're talking about irradiance, right? Okay, so now the irradiance is at 200 watts per meter square, and it has moved from 200 to 1000 watts per meter square. Now look at how the current has changed. It has moved from maybe 0.6 to 3 ampere, right? Now look at the voltage. The voltage has only shifted slightly from 200 to 1000, and the voltage has shifted slightly. Just to tell you that the voltage remains fairly stable once the sun is out. But what changes significantly is the intensity of the sun. That is the current, the amperage. So this is how, this is just an explanation of how intensity or irradiance affects your solar output. Now let us look at impact of temperature. Impact of temperature on your panels. Now, this is the current axis and this is the voltage axis. Now, I want you to notice how great the impact of current is on the output of the PV module. Now we are moving from this is 75 degrees centigrade, right? Okay, just a moment. Okay, so as the temperature increases, now this is what we have here is minus 25 degrees centigrade, and it moved to 0, it moved to 25, it moved to 50, it moved to 75. You can see how the voltage has dropped because of temperature. The voltage has dropped. So the lower the temperature, the higher the voltage, the better the voltage. So once the temperature begins to increase, the voltage begins to drop significantly. But look at the current. The current has not moved much, right? So temperature does not really affect current so much. It affects voltage so much. What affects the current is the intensity or the irradiance. It affects the current, but temperature does not affect current. Temperature affects the voltage. So let's look at standard test conditions. Standard test conditions. So due to the variability of power output of the PV cell, depending on the parameters such as irradiance and temperature, the performance of different cells operating under different conditions cannot be compared easily. So the thing is that when you look at the PV module and it's rated 300 watts, right? On what condition was it rated 300 watts? Because the operating conditions can vary. It does not mean that if you take that 300 watt PV panel and put on a roof, it will generate 300 watts. No. It cannot generate 300 watts. It can only generate 300 watts if it's subjected to the same condition, which we now refer to as the standard test condition. It can only generate that 300 watts. It can even generate more than 300 watts, depending on how you play around with the parameters. If a solar PV panel is rated 300 watts, there's a possibility it can generate more than 300 watts. And it can, but in most cases, it generates less than 300 watts, and which is why we'll talk about performance ratio. We're going to come to that. Okay. So in order to enable meaningful comparison between PV cells or PV modules, the rated output of PV cells or modules is always measured under specific conditions. So this specific condition remains the same, whether you're in Africa, Europe, America, or Asia. wherever that specific condition, so you create the same specific condition and you test it under the same condition, and then you can now rate it, and you can now say, okay, oh, this PV panel can produce 300 watts. So all those 300, 450, 600 watts are what they can produce under standard test conditions. We're going to see all those standard test conditions anyway. So the rated output of a cell or module is always measured under specific conditions. These conditions are standardized across all testing facilities worldwide and are called standard test conditions. Now, these are the conditions. These are standard test condition parameters. One of them is light spectrum, or AM, under 1.5. Then you have irradiance. The emphasis for us here is more on the irradiance and the cell temperature. So the irradiance is 1,000 watts per meter square. 1,000, please pay attention to this irradiance, because we are going to use it when we are going to be talking about peak sun hours. Peak sun hours, you see, we are going to always make reference to this irradiance, this 1,000 watts per meter square. Now, when the sun comes out in the morning, it does not mean that the sun is 1,000 watts per meter square. It's depending on your region, depending on where you are in the country or in the world, it is possible that the sun in your region might be 1,000 watts per meter square, okay, or less than that. Okay, but for you to say that this panel is rated 300 watts, you must subject that panel to 1,000 watts per meter square before you can be able to say it is this, okay? Now, another one is the cell temperature. The temperature of the panel has to be 25 degrees centigrade for you to, before you can say, okay, it is. So if you subject the panel to 25 degrees centigrade to 1,000 watts per meter square and light spectrum of 1.5, whatever output it gives you, that is the rated capacity of that panel. And this is something that is done, within seconds. So each finished PV cells or PV module leaving the production line undergoes a flash test. It is exposed to a flash of light under careful control of the standard test condition parameters, lasting only microseconds, and the output performance is recorded. So this output performance is what will now stick on the panel. So subsequently, the cells modules are sorted and sold according to, I think I've explained all of this, and that's what when you look at your PV panel, it is rated. The rated power is peak, maybe watt peak or the kilowatt peak. These are the output at standard test condition. Let us look at temperature coefficient. Now, I told us that temperature affects the output of your PV in terms of voltage. It affects your voltage, and once your voltage drops, it reduces the power output. So the temperature coefficient shows how voltage or current, or power output of a PV cells or module changes with changing temperature. So module data sheet gives temperature coefficient. So you're going to see this temperature coefficient at the back of your PV module. When you look at the data sheet, you see the temperature coefficient for open circuit voltage under standard test conditions, short circuit voltage under standard test conditions, and the power output at maximum power points. So the voltage temperature coefficient is the most common one that is used. Inverters and other devices such as the charge controller can be damaged by modules or string voltage that exceed the specified input voltage of these inverters. We've done an installation, and we after 2 days we got a call that something is wrong with the inverter, and by the time we got there, we found out that the voltage it was loaded. I mean, the voltage, it was the function of a voltage anyway. Yeah. So now there was a slight mistake, because we didn't put voltage protection when the installation was done. And this is important for every one of us who is going to be doing installations. You might also look at how you can also protect those equipment by putting a voltage protection. You could put what do you call AVS, voltage switch. Voltage switch, so that if the voltage gets to some certain unwanted limit, it just cuts off the supply into the system. So voltage is very, very important. I'm just stressing this just to make you how important voltage is, when you're doing your installations. So the distance can be damaged because of voltage if it either exceeds. If it's lower voltage, if you have there are some certain minimum voltage that this needs to operate. And in some cases, if the voltage didn't get to certain minimum voltage, it can also damage the equipment. it's not only high voltage, low voltage can also damage this equipment, especially some of these new modern inverters that we have today that are not transformer based. That's by the way. So where are we? So the voltage is too low, and this can cause system underperformance. Okay. So now voltage temperature coefficient, what this simply means is that to what level will the performance of this PV module, to what level will it reduce if temperature increased by 1 degree centigrade? So if you increase temperature by 1 degree centigrade, how will it reduce the voltage of the panel? So if you can determine that, you can actually see how the power will drop if temperature keeps increasing, right? So voltage temperature coefficient, I give it in the form of maybe minus 0.15, this is an example, 0.156 voltage per degree centigrade. So every drop in degree centigrade will lead to drop in voltage by 0.156. Every drop in temperature will lead to this. So this is what it means. It can be millivolts, that's MV, okay? It can also be expressed as percentage. So what percentage of the voltage will drop for every rise in temperature or every drop in temperature? So this is how they are rated. So so change in temperature also affects current, but it is not significant. It is small, right? So if you look at this example here, you can see that for every rise in temperature or for every change in temperature, every unit change in temperature can result to 0.0029. So we find out it is not significant compared to a voltage of 1.5. And the combination of these two actually gives you the power temperature coefficient. So this is a calculation exercise. Assume the following data: the yearly daytime temperature at a location changes from minus 10 degrees centigrade to plus 45 degrees centigrade. A PV module is being installed, which has, now this is the ratings at standard test conditions. So open circuit voltage of that system is 43.24 volt at standard test condition. Then, but the maximum power point is, so the maximum power point voltage is always lower than the open circuit voltage. Remember that the open circuit voltage is the maximum voltage of the PV when current is 0. And the maximum power point is the point where you can generate the highest amount of electricity output. So the maximum power point voltage is 35.35 volts at standard test condition. So a temperature coefficient, now they give you the temperature coefficient of -0. So for every degree change in temperature, whether plus or minus, your voltage is going to drop or increase by 0.168 volts, okay? So note the temperature coefficient, that is temperature coefficient at maximum power point voltage, is slightly different than, I think I've explained this already. So this means that so this, like I said, some of these write-ups are just to explain what I've already discussed here. So when you read it, you understand. But this is an exercise, though. So these are the calculations. And because of time, we will not go line by line through these calculations, but they are also simple calculations. If you understand what I've explained about voltage drop, you understand this calculation. So let me just go through this first one. What will be the maximum open circuit voltage produced by the module? The maximum open circuit voltage produced by, so the maximum open circuit voltage will be produced at the lowest ambient temperature, which is minus 10 degrees centigrade. So the lowest cell temperature will be minus 10 degrees centigrade. So the open circuit voltage will, at minus 10 degrees centigrade, would be the given voltage. You remember that, let me go back to this. Remember that our open circuit voltage at standard temperature is 43.24. Now, this is the catch. Standard temperature is 25 degrees centigrade. Standard temperature. But now this question is asking us at minus 10 degrees centigrade. It's not asking us. So if you change the temperature from 25 degrees centigrade to minus 10 degrees centigrade, what will now be the open circuit voltage? So remember, for every change in your voltage, you are also given a value, which is 0.168 0.86. For every change in your temperature, this is how the voltage change. So you have to do 25 minus 10. You find out the difference between 25 and minus 10. You now times it by this. You now add it to your given open cycle voltage at 25. Then that will give you the, so you're assuming that you're operating that PV module at minus 10 degrees centigrade. Your open cycle voltage will now be 49.14 volt instead of 43.24 volts. This might sound a little bit of technical for some of you, but I want to guarantee that it is not difficult. Okay, this is for those of us that really want to maybe kind of dive a little bit into the technicalities. Otherwise, it might not. It's important to know about this anyway. So this is the exercise that we have, and the solutions are there. Please, I just try to explain this first one so we can understand how the solutions apply. So because of time, let's move ahead. So let's talk about orientations and inclination, or rather tilt of PV modules. So when you go out for installation, you begin to wonder, how do you orientate your PV modules? How do you incline it? What angle, what tilt angle should it be? Is there a standard way of doing this? Yeah. So we're going to talk about this in this section. So PV module orientations and inclination. When we talk about inclination, we're talking about the tilt angle. Significantly affect the amount of irradiation that the surface receives, and hence the amount of energy that the module produces. Now, in the northern hemisphere, now we have north and southern hemisphere. Depending on where you are, Nigeria is in the northern hemisphere. In fact, we are closer to the equator. Now, this is more like a geography, but it's important when you want to install PV systems. I'm sure some of you have, you should have like a compass in your phones that you can use to actually maybe say where the north south is, but that is the cardinal directions. It's different from the northern and southern hemisphere. Nigeria is in the northern hemisphere. We are somehow closer to the equator. So if you're in the northern hemisphere, your PV panels should face south. Is a principle. Nigeria is in the northern hemisphere. So your PV installation, try as much as possible to make sure your PV installation faces the south. So the PV module should be facing south. So if you're in the southern hemisphere, then your PV module should be facing north. That is one of the cardinal principles in your PV installation to get the maximum output for your PV system. So this guarantees the maximum irradiation level on the PV module throughout the year. In regions closer to the equator, Nigeria is closer to the equator, like I said, the orientation is less important. So if for example, if your country is on the equator, the best way is just to put your PV flat. Just put it flat. But again, it's not it doesn't make rational sense to put your PV flat because it can absorb dirt and debris, without self-cleansing. So I think I have explained that. So the optimum tilt angle for PV modules depends strongly on the location. As a rule of thumb, the module should be tilted. Now we are talking about tilt angle. The module should be tilted to an angle equal to the latitude of the installation site. Now we're talking about tilt angle. We've spoken about where you're going to face your PV panel. So in Nigeria, your PV panel should face south. So Nigeria is located on a latitude of between 4 and 14 degrees. So your PV panel, your tilt angle should be between maybe 4 and 14. Maybe you can do 15. Okay, so you don't need so much tilt angle for your PV panel. So, but again, the rule of thumb is that your tilt angle should correspond to the latitude of your installation site. So you might want to check Google to find out what is the latitude of your installation site. Like I said, Nigeria, if you're moving from the southern part of Nigeria, Rivers, Bayelsa, it's around 4 degrees. But if you move up to the northern part of Nigeria, it's about 14 degrees. That's why I said Nigeria is between latitude of 4 and 14. So, but of course, in anywhere in Nigeria, you can decide to put maybe 10. right? Because it is important to allow for self-cleansing. So if anything falls on the PV module, it can fall off. Yeah, don't allow it to be flat. So I've talked about roof mount, where I say that if your roof is already, if you're installing on a roof and the roof is already tilted to a certain angle, you cannot ask the owner of the house to go and change his roof because you want to install solar panel. So you just have to use the tilt angle of the roof to install your solar PV panel. So in regions closer to the equator, the most solar radiation is captured if the PV panel is flat. However, in practice, a minimum tilt angle of 10 to 15 degrees is recommended to allow for self-cleansing. I think I've explained this already. So this is like the globe. This is the equator, for example. Nigeria is somewhere here in the northern part. So this is the northern part of the hemisphere, and this is the southern part of the hemisphere. So Nigeria is somewhere around here. And that's why when we are doing our PV installation, it has to face south. Okay, it has to face south. So this is just to throw more light on the orientations of PV panel. So let us look at the solar yield estimation. How do you estimate the energy that will come out from your PV system? So in order to assess the energy yield of a PV system, one has to know about the available resource input. The available resource input is basically solar radiation. So you may need to have a solar radiation map, of Nigeria or wherever location you want to do your installation, and then see how the sun intensity of the area is. Because this will be important when you want to do some calculations, when you want to make some assumptions. That's what we call peak sun hours. So these are just based on some certain assumptions that, okay, so for example, in Nigeria, if you're doing any solar project around the northern part of, around the southern part of Nigeria. So if you look here, you see that this is the southern part of Nigeria. You see that the radiation here is not so strong than the northern part of Nigeria. So in your solar yield estimation, you could use something like 4 peak sun hours could be 4 in this area. So I'll be surprised if I see someone who is designing for a system that will be installed in the southern part of Nigeria, and then you're using something like 6 as your peak sun hour. Obviously, for me, that's an overestimation. Now, this is the northern part of Nigeria. You have higher solar radiation in the northern part of Nigeria. So someone can use 5 or 5.5 or thereabout, right? So these are subjective, but of course, it has to be based on realistic, assumptions. So color-coded solar resource map provide the first indication of available solar energy production. I think I've already explained this. The economic feasibility of PV plant critically depends on its electricity yield, which in turn depends on both the meteorological condition at the location and the performance of the PV plant. So as the electricity yield is heavily dependent on solar irradiation level, it is essential that the accurate and long-term climate data are available for the given location. Solar irradiation at a site is often stated in terms of peak sun hour. I already tried to explain this. We are going to explain this with a diagram in more detail. Peak sun hour is important. It's an emphasis here over a certain period of time. So let us go ahead. I mean, please pardon me. I will skip some narration because while I'm making this, I really don't enjoy reading what I've written, because the reason why I have them there so that when you're doing your self-study, you can also read them. Otherwise, I wouldn't need to have those right. I'll just put diagram and explain. But I have to put those right up so that when you're reading, you can also, make sense of what we are trying to push across. So let us look at performance ratio. I think I have mentioned this earlier before when I was talking about standard test condition, right? So performance ratio is how your actual performance of your PV system deviates from the standard test condition. So your PV panel is rated 300 watts, for example. It does not mean it's going to give you 300 watts, but your performance ratio is what tells you how it has deviated from that standard test condition, right? So it's rated in percentage. So if I have a PV module and I say maybe after installation and I take my measurements, what it's producing to compare to what it should have given me under standard test condition, I can now come and say, oh, this PV panel is performing at 75 performance ratio. That's, so what that means that 25% of what I should have gotten at standard test condition is eroded. So it's minus, so that is minus 25. So its performance ratio is 75. When you do your PV6 analysis, you're going to also see this. It's important to understand all of this technology, because by the time we run you through some of the PV design softwares, these are some of the outputs that you will be seeing. So it's good to understand what they mean. Performance ratio, what does it mean? So it's one of the most important parameters for assessing the performance of a PV plant. It is the ratio of actual plant output to nominal plant output at standard test condition. And how do you do this performance ratio? Performance ratio is equal to the actual output. So performance ratio is something that is best done when you've installed your PV system and it has operated for a certain period of time. You can now measure the actual output of your PV system. You're now divided by the theoretical output at standard test conditions. So whatever you get, it expresses in percentage, and that gives you your performance ratio. So a lower performance, it's okay.
I wanted to say, hello, Chima.
Okay.
I wanted to say some of us should just see it as a safety factor. As engineers, we always make use of this issue of safety factor. So I think some people should just have in the back of the mind that it's more like a safety factor, but downscaling safety factor, let me use that word. Okay. In some designs, we do upscaling. If you got something for 100, you're scaled by 1.2. But in this case, it's like you're playing, you're teaching towards the worst case scenario. So let's also see it as a safety factor, the performance ratio. Thank you.
Thank you, Engineer Uche, for that input. So a low performance ratio is indicative of high system losses. So if you have a low performance ratio, it's an indicative of a high system loss. That high system loss could be as a result of high temperature. So you might want to see what is the reason why you're having a low performance ratio. It could be that the temperature on the ambient temperature of the PV panel is high and it's affecting the voltage, and then the output current and output power is eventually reduced. Okay, so for example, due to high module temperature, reflection of the solar irradiation and what have you. So in contrast, performance ratio is also used with common reference value to the planning stage of a PV system. For example, I think I've already said it, when you're doing your PV design. So when you're doing your PV design, perhaps you might not be able to know what the performance ratio should be, just like Engineer Uche just rightly explained. You might use it as a safety factor, so you don't overestimate, especially when you're doing an investment grade assessment. Okay, so people want to invest based on what you have told them. And as an engineer, you don't want to finish your design and you tell somebody that, look, make this investment. This is how much power your electricity you're going to get out of this investment. And of course, you know that it's only the output you can sell. It's the electricity that output from the PV system that you're going to sell and make money. So, but when you overestimate that electricity that your investor is going to sell to make the money, and then the investor now make that investment and is not seeing that money, it means you've deceived that investor. Maybe not knowingly, not intentionally, but because of your unprofessionalism, or how do I put it, incompetence. That's why it's good sometimes. It's a safety net, it's a safety factor. It's better you slightly underestimate than overestimate. So that if you use a performance ratio of, example, 60%, and then the investor still feels comfortable, and then in reality, the actual performance ratio is 65 or 70, then kudos. You'll be, the investor will even, be happy with you, right? Then, when the case is the reverse, when you estimate, when you use 70% performance ratio, and then in reality, the performance is 65. So it's like a safety net, just like Engineer Uche explained. So once the energy yield system has been estimated, the revenue from the electricity sale, I've explained this already. So let's just move ahead. It's already 12, but in the next 20 minutes, we should run this up. Energy yield calculation and example. I mean, ideally we should end by 12, but of course we spend extra time. I hope we wouldn't mind, please. Let's just give it another 20 minutes. But subsequently, in other Saturdays, we are going to comply to our time. So let's ride on for the next 20 minutes, please. So energy yield calculation and example. So the following equation provides a quick and simple way to estimate the energy yield of a PV plant over a particular period of time. Like I said, what you're actually going to say is energy yield. I mean, most investors don't care about kilowatts. They don't care about panel. They don't care about, just how much am I going to make if I put this investment? They want to see it in Naira and Kobo. So it is you or it is we who are the engineers, who are the technical people who have to go and do our analysis, do our technical and economic analysis, and then translate all of this analysis to them in Naira and Kobo. So this is one of the things that we can do for PV system. So energy yield is equal to peak sun hours times your rated performance, that is peak performance, times your performance ratio. Now, this peak performance is your rated power of your PV system. If you have a 10 kilowatt PV system, so your peak is 10 kilowatts, then your performance ratio is you can assume 65 performance ratio. Okay, like I said, it's somehow subjective, but of course it will be it will be subjected to reality check, after your project has been completed and after maybe the project has been completed and it has operated for some certain period, then that's your assumption will not be subjected to reality check. So it's important that you try as much as possible to put something that is close to the reality check when it calls. So this is just an explanation of the E. E is the energy yield, the peak sun hours. I will explain that, I think, in the following slide. I will explain what the peak sun hour is, but let's pretend like we know what the peak sun hour is. For some of us that don't know, just pretend like we are going to explain that. Then we have the peak or the nominal power output of the PV plants at standard test condition. They have their performance ratio. I've already explained what the performance ratio is. It can be between 65 to 85, depending on the climatic condition of where you did your installation. So the peak sun hour is an imaginary case. Okay, I think I even offer some explanation here for the benefit of those who are not familiar with what peak sun hour is. So it's an imaginary case where the sun shines at a constant irradiance of 1,000 watts per meter square. Now, this 1,000 watts per meter square is coming back. Remember when I said you should keep an eye on it? So this 1,000 watt is your standard test condition, right? So we assume that when the sun comes out in the morning, so let me use Nigeria as an example. So when the sun comes out in the morning, okay, let me just give you this. I was working with a client, and I said, sir, peak sun hour that I have considered for this project is 4. I said 4. The man said, no, why would I say 4? That the sun comes out in the morning, by 9 a.m. the sun is out and the sun is there till 5 p.m. And if you calculate that, that is about 9 or 10, hours. You're like, so why would I use 4 that I'm trying to, I said, no. So I have to now begin to explain. So this same explanation is what I'm trying to offer here. So when the sun comes out in the morning, it does not mean that that sun is operating at 1,000 watts per meter square. It may get to 1,000 watts per meter square, maybe in the afternoon, maybe around 12 or 1. It may get to that point. It may not get to that point. It could even be 800 at 12 or 1. It could be 800. So when it comes out in the morning, it could be operating at 200, 400 watts per meter square. So if you look at the entire time that the sun is out, you might have like 10. But that 10 hours, if you compress it and shoot it up, that, okay, assume that the sun comes out and it's hitting 1,000 watts per meter square, if you can compress that 10 hours to just about 4 hours. So the sun comes out and it maintains constant 1,000 watts per meter square for only 4 hours. But you can drag that 4 hours, you can spread it to 10 and reduce the peak sun hours, maybe 400, 200, 300, 500. But if you compress it to 1,000 watts per meter square, it can only be 4 hours. I don't know if there's a diagram, but I just have to chip in this explanation so we can move on with it. Okay, so this is a diagram. Okay, I think okay, this is well organized anyway. So we can visualize. So now this is what I was trying to explain. The sun comes out in the morning. It didn't even, okay, even at peak period, at 12, it didn't hit this 1,000 watts per meter square. It didn't hit that 1,000 watts per meter square. Before around 8, and the sun is there until around 5. It goes down. So if you calculate the hours it has spent here, it's maybe this 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, about 9 hours. That does not mean it's peak sun hour. So the peak sun hour, we assume that it comes out, it hits 1,000 watts, and it remains at 1,000 watts until it goes down. So the area under this, shaded region of the sun part, this area is equal to this area as well. Okay, so this is what we call peak sun hour. So we just want to standardize it, because this is subject to, different regions of the world where you want to do your solar project. But we wanted something we can standardize. That's why we say, okay, peak sun hour is 1,000 watts per meter square. Okay, so for example, if the irradiance is 1 kilowatts per meter square, 1 kilowatt means 1,000 watts. That is at standard test condition. So how many sun hour is required to produce 4 kilowatt hour? So let us put that equation to use. So we have energy yield is equal to peak sun hours times peak times performance ratio. So if we make peak sun hours subject of the formula, you will not have energy yield, because we were given the energy yield here. Only that we are not asked to calculate. What were we asked to calculate? We should calculate the peak sun hours to produce this energy. Okay, so we were given the energy yield. In some cases, you'll be calculating the energy yield, but in this case, they gave us the energy yield. So the energy yield is 4 kilowatts per meter square. So we are not dividing it by the peak. So we are also given the peak, the irradiance of the sun, which is 1 kilowatt, 1 kilowatt per meter square. This is 1. So we can now, by our calculation, we can now say that it is 4 hours. Okay, now we assume that the performance ratio is 0. That is why I made this statement that assuming losses are neglected, we assume that performance ratio, we assume that performance ratio is 100 or 1 rather. This performance ratio, we assume it to be 1. Now, this is not a reality. This is just for explanatory purpose, please. So this is an example. A PV plant developer is planning 2 PV plants, one in Northern Europe and the other in Southern USA, and wants to estimate the energy yield of each to gauge their economic feasibility. So energy yield is very, very important when you want to do technical and economic feasibility. So we have an investor that wants to invest in 2 different sides. One is in Europe, Northern Europe, one is in Southern America. Okay. So let us calculate the energy yield from these 2 power plants. So in Northern Europe, the rated power of the project is 1,000 watts, 1,000 watt peak. In fact, both of them are 1,000 watt peak. But the peak sun hour in Northern Europe is 1,200 for 1 year. And the performance ratio is 0.8, that's 80%. So the energy yield is equal to the peak sun hours times the peak 1,000 watt times the performance ratio. So when you do that, we have peak sun hour of 1,200, 1,000 watts peak times 80%, 0.8. If you do that, you have 960 kilowatt hour per annum. So in a year, that system, if you make that investment in Northern America, you will have 960 kilowatt hour per annum. That same investment, if you make it in Southern America, that same investment, if you make it in Southern America, because they have a higher peak sun hour, 1,900. And even though their performance ratio is low, but they have a higher peak sun hour. So if you do the energy yield in that case, you will have 1,330 kilowatt hour per year. So if you're the investor, where would you invest? In project A or project B? Please, I want this to be interactive. Somebody should.
Project B, of course.
Okay, thank you very much. So it is obvious that you invest in project, because in project B will give you more energy that you can sell to make money. So this is why it is important to have this technical skills to do feasibility, to calculate what energy yield of any PV production, PV installation would be. So let's look at load profile. I think we are gradually coming to an end. In the next few minutes, we'll end this. So let's look at load profile. For a successful electrification project, it is necessary to conduct a precise analysis of expected electricity demand, as it has significant impact on the design and cost within the project. So when you want to do a PV project, sometimes you may want to do a load. If you have a load profile, fine. But of course, we know that we are not very good with data in Nigeria. But if you have a load profile, that will be perfect. You look at the load profile and look at the peak. Okay, even when you're sizing your generator, and it's a very big mistake that we do when we are sizing our generators in Nigeria. We look at the peak and we do not investigate the cost of that peak. If maybe the cost of that peak can be shifted, maybe there is pumping machine that comes on when cooking is going on in the afternoon. When electric cooker is on in the afternoon, somebody owns the pumping machine, and it creates a spike in your profile. Let me show you what a load profile is. So this is what a load profile is. So this is night. When money comes, equipment begins to increase, come active. You know, your evening time is usually your peak period, and it begins to die down again, right? So now this is your peak period. This is a load profile. This is a typical example of a load profile. Now the question, when you have this kind of, you may want to investigate what is the reason why you have this peak profile. It is possible that if the pumping machine is what is causing this, for example, okay, you could actually say, okay, not on the pumping machine this time, on it anytime here. So you can reduce your capex, your capital investment in your solar project. So the system should neither be unnecessary when you're designing your systems for solar PV. It should unnecessarily be oversized or undersized. You know, therefore, electricity generation and electricity demand should be in balance. That's what we usually call demand supply optimization. Okay, in electricity market, you have to try and balance demand with supply. Okay, if you don't do that, you have inefficiency in the system, and somebody has to pay for that inefficiency. And in most cases, the customer are the one who are going to pay for the inefficiency. That's why when you go to America or some other country, when you see your electricity bill, you know, maybe for industry, I don't know if it's for, but when you see there is what called demand charge. They will charge you for demand charge. They will charge you power factor penalty. There are so many things that are included just to make sure you consume electricity responsibly, right? Now, that's aside anyway. Let's come back to as it relates to PV system. But it's also important in PV system. And the reason is this. You have to try and optimize the system so that you don't, so your clients don't have to spend so much capital expenditure on something that could have been avoided. That's why it's important to look at your load profile and then advise the clients. So for some people, before they install PV system, they will go and change their AC and put inverter air conditioning system. So that is trying to reduce their load profile so that they can have a lower capex on their PV system. So that is the idea here, right? Some people, they might want to change some of the equipment in their house. Some people may want to change their fan, you know, to a more energy efficient fan. Some people may want to change maybe one or two things just to reduce the load. So that is the idea of looking at your load profile. I've explained this load profile already. This load profile is like a day. It's 1 day load profile. So when you aggregate this over a month, this is how it may look like. So I have explained what the importance of this peak, how you can do your peak shifting, and so you can have a lower capex. So thank you very much for your active participation and allowing me to lead this discussion. Like Engineer Uche said, nobody knows it all. In as much as I'm leading this discussion, you know, I also want to learn from you, you know. So in our subsequent classes, I will encourage you to share your experiences. I heard somebody say that he has done an installation and the customer keep coming back that something is not working as designed or as expected. I mean, so let us, so we also want to hear from you. If there are areas you want us to improve along the line in the way we are delivering this training, please, we are open for recommendations. And like I said, please, I like classes being interactive. So in our subsequent class, let's perhaps this one is just an introduction. When we get into designs and calculations, in that case, I mean, it can be more interactive. So thank you very much. I have come to the end of today's presentation. Thank you for your active participation. Do you have any question? Engineer Uche, did you look through the chat to see if maybe somebody has dropped a question?
Yeah, just one question, and I didn't quite understand it, but I've explained what I understand from basic physics about the impact of temperature. Just say it once again in 1 minute. The effect of temperature, higher temperature on voltage and current. That's just it.
Okay. So when you have a higher temperature when we talk about temperature, we're talking about ambient temperature. That is the temperature around the PV panel. So the weather temperature might be different from the temperature on the PV panel. In fact, the temperature on the PV panel is actually higher. So if the ambient temperature, for example, is about 45, just know that the temperature of the PV panel might be about 70, that is plus 25. Okay. So now that is the temperature of the PV panel. So once the temperature increased by 1 degree centigrade, it reduces the output of that PV panel by a factor, which is what we call the voltage coefficient of voltage, right? So for every rise in temperature, there's a factor that the output on the PV panel will drop. And that is how temperature affects the output of a PV panel.
Yeah, that's what I said. In summary, higher temperature leads to low output. And output is the energy, is the power, sorry. And power is a function of voltage and current. So voltage from Ohm's law, voltage and current gives you the power. So one of them will be affected. All right. So I think we are in question and answer session now. Let us get feedback from us. Any question?
I think
good afternoon, everyone. Thank you for the comprehensive lecture, or how do I call it? We appreciate you. My name is Odunayo, and from today's class, I'm sure maybe the subsequent class, I typed it on the chat. Maybe we are going to look at the storage, because if you look at the solar system, storage is of a major concern. And like we all know that storage is a function of hours, and that determines even the size of the storage. And at the same time, how are we going to balance the storage with the loads that are inductive? And what do I mean by inductive load is any motor-driven equipment. For example, when you were showing us the load profile, you show us where we look at the pump, and you were trying to advise us that even for generators, that most time a lot of us oversize or undersize, because we need to study the load profile and the pattern. So okay, when is it the normal time that they normally use, for example, pumping machine? So you use the pumping machine, which is an inductive load, to balance maybe other residual load at that time. So like I said, I believe it's not more of a question, but it's more of like a contribution and an expectation, because most time we find ourselves in a situation that when it comes to the storage, and the client is saying, okay, I want this design, and I want 6 hours, I want 7 hours. So how to now balance it with generator and the supply from the discos now? So becomes a kind of issue. So I believe we'll take it off from there. Thank you very much.
Okay. What you just said is what we'll be doing next week. Next week, we'll be going into the design proper. Today is just to lay a foundation. And before Samuel says something, I want to bring us again to this material on my screen. We have it already. I think I've shared to everybody. This material is very important for us to gain speed. It's called Energy Analytical Basics. About 50 pages of it. We would like us to...
Sorry, why Engineer Which is speaking about this, I just want to add my voice to the emphasis he's making on this material, because I had the last speaker, talking about different kinds of load. You have resistive, you have capacitive load, you have inductive load. When you go through this material, you're going to see how we analyze, okay, which is even going to that point where we have those different kinds of load and how it affects your electricity quality, your power quality. Which I keep going, I think you'll get to the point where we'll have those kinds of load. So it's important that you also go through this material. Thank you. Engineer over.
Go through them so that let us be aware that there was a lecture we are supposed to hold, like a foundation class, but it's something we also know that if we commit our time to it, we'll grasp it. So Chima, what I'll suggest is that we're going to release these materials and then we're going to come up with a small calculation that our participants can do. I know most of them are business people, they might not have time, but at least if it means 10 questions so that we can use it to see how far they have gone through these materials. So gentlemen, we're going to give a small assignment on these materials, right? Calculate power, voltage times time, KVR, inductive load, you mentioned it, non-inductive load. So I think we should
Engineer, sorry, I mean, just keep going. I think there are a lot there are questions, even with solutions in this material that they can try on. I know even at the time we had this training on this very material, we didn't have all the time to go through all the questions that we have in it. Keep going there. There are some example questions that they can,
this BA example is very, very important. The reactive power, the real power, and the apparent power. Anybody who understands this, especially within the context of what we're discussing, it will go a long way in helping you to size, to know the sizing, the dimensions of your battery, the rating of your battery. Most things is that when you are into the energy space, you must know how to use the terms and terminologies associated with the energy space. So that is that. So what we're saying in essence is try and go through these materials so that we don't have to spend one Saturday going through it again. Okay, as Engineer Chima said, there are some questions that are there. So I think those questions are very self-explanatory and they will really help us. Okay. All right. Any other question? Engineer Samuel, you can ask your question now.
Yes, thank you very much for your presentation. Mine is just more or less like a request. Please, I know you've mentioned it before that if we miss any of these classes, that we shouldn't too much panic that the materials will be shared. My request is